Okay, we're on to number 3 now, which is really number 2 with a complication. So in number 3, instead of the concentration being 0 coming in, this is the only thing that's been changed. It's 0.5 gram per gallon. So now we have salt coming in and salt going out. So what's going to happen? Now let's find out. So we go back to our differential equation. We're looking to set up an initial value problem, which is a differential equation and an initial condition. And this is going to be whatever is coming in minus whatever is going out. So now we do have something coming in. It's 0.5 grams per gallon at 3 gallons a minute, which means we're going to have 1.5 grams of salt per minute entering the system. The stuff going out is the concentration. The volume is constant because it's 3 gallons in, 3 gallons out. So we have the constant volume of 100 gallons. We have whatever the concentration is at that time times the 3 gallons per minute. This is 100 gallons. So these gallons cancel out. So our differential equation then is dm dt equals 1.5 minus 3 over 100 m. That's what we had before. Let's write it a little differently though. So it's dm dt plus 3 over 100 m equals 1.5. So now we have our first order linear inhomogeneous equation, and we also need an initial condition, so m of 0 is 35. And then this is our initial value problem, IVP, initial value problem. So that's what A asks you to do. Now B is to solve it. Now the way we solve this problem is to first solve the homogeneous case, but we've already done that. M of t is a constant times a decaying exponential. This is the general solution to the homogeneous equation. To find the general solution to the inhomogeneous equation, we suppose that m of t is a function, an unknown function, question mark, times that exponential, and then plug it into the inhomogeneous equation to obtain a condition on A. All right, let's do that. So if we take this and then plug it into this differential equation, what do we get? Well, we're going to have A prime times the decaying exponential plus A times the derivative of that decaying exponential. And both of these terms constitute dm dt plus 3 over 100 times a e to the minus 3 over 100 t. Okay. This is m equals 1.5. And now there should always be some canceling. Move the camera a little bit. So these two terms cancel, and this leaves us with, straightens out a little bit, with a prime e to the minus 3 over 100 t equals 1.5, or a prime equals 1.5 e to the positive 3 t over 100. So then a is going to be 100 over 3 times 1.5 e to the stuff plus an integration constant, right? So just integrate. This ends up being 50. So then A is 50 e to the 3t over 100 plus c, but we're not done yet. This is only part of what we need. We have to go back up here to what we suppose the solution to be. Now we have A, so we have to multiply by this decaying exponential to find m. So do something like this. So now m of t is then 50 e to the 3t over 100 plus c times the decaying exponential. So this is 50 plus c e to the minus 3t over 100. Now apply the initial condition. We initially had 35 grams. So this is equal to 50 plus c. So c equals minus 15. So now, let me pause for a second. This is the general solution to the inhomogeneous equation. What I'm about to write down is the particular solution. So this is the particular solution. Does this make sense? Well, there's a couple ways we can think about this. So one, the limit of m of t as t goes to infinity is 50 grams. So the idea is that the tank is going to increase. Now let's think about this. Let's see if we can make any sense. The concentration is 3.5 grams per gallon, right? So 3.5 grams per gallon. No, per 10 is 0.35. So initially we have 0.35 grams per gallon. This is the initial concentration. So every minute we're losing 3 times that, which is 1.05 grams per minute. That would be the initial rate lost. Now, if we have 0.5 coming in, right, then our initial rate coming in is 1.5 grams per minute. So right from the get-go, there's more coming in than is leaving. So that's going to cause a buildup. Now, at some point, things are going to balance. This is the 50 grams. At some point, because if we're adding more salt, then we're taking more salt out as well. Where does that balance out? So let's see what 50 does. If we have 50 grams in here over 100 gallons, then that's 0.05 grams per gallon. Well, at 0.05 grams per gallon, then you're losing 1.5 while you're getting 1.5. So 50 grams makes sense. Anything under 50 grams and we're gaining more than we're losing. But at 50, it's just right. So these is 1.5 grams per minute of salt entering, there's 1.5 grams of salt leaving. So this makes sense. Makes sense. And then as a follow-up, so I think this was C, I think. This was B. D, how long does it take before you're at 95% of 50 grams? Well, that's easy to solve. You just do 0.95 times 50 equals 50 minus the 15e to the minus 3t over 100, and solve. T will end up being about an hour. It's in minutes, so it'll be about 59 plus minutes. But it takes about an hour to get pretty close to there. All right. So again, try to make sense of your solution. Does this make sense? Does the minus make sense? Sure, we start at 35. As this goes to 0, we get closer and closer to 50 from below. It makes sense.